Thank you, Nicole, and thanks to the organizers. It's my first time in San Sebastian, and I like it very much. As Nicola said, I'm currently at the University of Liège in Belgium, but it is very recent, and before I was in Nicola's group, and this work is from this time, so that's why you see all the corresponding logos here. So I'm going to talk about Phonon-limited transport in 2D materials. And the background story is the following. A couple of years ago, the 2D team in Nicola's group have published this paper in which we show how we built our database of 2D materials starting from known 3D compounds, experimentally known 3D compounds. So we used geometrical algorithms and Van der Waals DFT to figure out which materials were layered and then which were exfoliable. We found quite a few. And eventually, everything I'm going to talk about today is intended to be applied on this entire database. But the results I will show are more about a smaller set of materials that are easily exfoliable, so their binding energy is relatively low, and they have a small unit cell, so less than 6 atoms. And the good thing with those materials also is that there are a range of physical properties, band structures and phonon dispersions in particular, already available publicly on the Materials Cloud. Then different members of Nicola's group have been, or the 2D team, have been looking at different properties for various applications. But my focus was on electronic transport. And so my question was, can I find among this database of materials those with outstanding transport properties? And before going into the details, I'll tell a bit more information about the context and the objectives. So we are talking about Phonon-limited charge transport in gated 2D semiconductors, so only phonon scattering. Then we'll talk about quantities like conductivity, mostly conductivity in this talk. And we are looking at materials that are doped, and the doping is done with gates, as in a field effect transistor. And finally, we are looking for materials with a gap, because it's interesting for certain applications. The objective is to find materials with high conductivity. Here I put a number for the record room temperature conductivity of graphene, but remember that it has no gap, and so what we're trying to do here is to get as close to this exceptional material as possible, but with a gap. And why are we doing all this? There are several applications that would benefit from a highly conductive semiconductor for logical devices or optoelectronics, for example. Also, more generally, we're interested in the physics of electron phonon scattering in 2D. And finally, from a materials science point of view, it's a very challenging yet interesting question to ask oneself, are we capable of pinpointing a certain property within thousands of materials in the database? So to do all this, we developed a certain set of tools. And the first one that I like to talk about is the most fundamental one, is the one we use to compute electron-phonon interactions. And this is density functional perturbation theory for gated 2D materials. And those systems have two peculiarities that are dimensionality and field effects, and those things do have consequences on electron-phonon interactions, so we need to take this into account properly. The first thing we need to deal with is dimensionality, and the issue is that, as you know, plane wave codes like quantum espresso rely on 3D periodic boundary conditions. So when you simulate a 2D system, you actually have periodic images of the system, and this can be a problem, especially for phonon perturbations, because they can induce some long-range Coulomb interactions between the periodic images, and you're not simulating a 2D system anymore. The solution to this is to truncate the Coulomb kernel in between the periodic images. This idea has been around for some time. We just extended it to density functional perturbation theory to do phonons electron-phonon interactions. And note that we've shown this to be particularly important to treat polar optical phonons, both for their dispersion and their coupling to electrons, and as you can see in those two papers. Okay, the second thing we need to deal with are the electrostatics of the field effect setup. So that's when you put gates around the material to try to dope and induce some charges in it. And this is actually relatively easy to do once you have the proper periodic boundary conditions. We just add to the Kohn-Sham potential those gates potential, which are represented by simple charge planes. Okay, so this has been implemented in Quantum Espresso. The second tool I'd like to present is the transport workflow, and this is what we use to do high accuracy calculations of conductivities. So transport properties in general are relatively complicated to compute. They require many expensive calculations and a lot of parameters, and in the end, a lot of both computer and human time. And at this point, I should say that there are, of course, other existing methods to compute transport properties. And so in this slide and the next two, I will try to focus on what we do a bit differently and what are the strengths of our approach. Starting with automation. So we've put a lot of effort into trying to reduce the human time involved by automatizing the process. And this is done with AIDA, which I'm guessing a lot of you know, is a code that allows one to deal with high throughput calculations, data management, and automation. So the automation part works with workflows. There are basically scripts that tell AIDA what to do. You still need to work on those scripts, but if you can make them general and robust enough, then you can just let AIDA work, and you gain a lot on the human time. In the case of transport, what the workflow does, it first starts with from basic information that we already have in the materials cloud, so electronic band structure and phonons. Then it identifies the electronic states and the phonons that we need to describe electron-phonon scattering. It computes all the electron-phonon coupling matrix elements and then plugs all this into the Boltzmann transport equation that is then solved to get the conductivity. Okay, the second thing we do a little bit differently is the sampling. So we do not sample the entire Brillouin zone. Instead, we focus on the states that are relevant for transport, and those are around a certain energy window around the Fermi level. And the size of the energy window is determined by the temperature and the energy of the highest optical phonon. Then the workflow identifies, so in an electron-phonon scattering event, you have an initial electronic state, a final electronic state, and a phonon that brings one to the other. The workflow identifies the initial states, the final states, and then all the phonons needed to go from any initial state to any final state, and then reduce the phonons by symmetry. A last practical point that is interesting is that all those grids can be chosen to be different. Then the workflow takes care of mapping everything on or interpolating between grids. Okay, the last part of the process is the solution to the Boltzmann transport equation. So here we want to find the linear response of the electronic occupations with respect to an electric field that is driving the current in the presence of scattering, of course. And what you end up with is a system of n coupled equations, where n is the number of electronic states, and the unknown is this tau here. It has dimension of a time, and I will call it scattering time, but keep in mind that there are different definitions of the scattering time. Here it's just definition within this, defined within the set of equations. Then there are different recipes to solve this set of equations. We chose to solve it iteratively for more accuracy. And another point that is very important for us has to do with how we deal with those energy conservation delta here. We do not use Gaussians to integrate them. Instead, we use the triangles method, which is nothing else than the equivalent of the tetrahedra method, but in 2D. And this is important for us because then we don't need to do any convergence test on smoothing parameters, and this is much better for automation. All right, so that's it for the transport workflow. This is still something aimed at accuracy, and even though we reduce the human time quite a lot, there is still non-negligible computer time involved. And this is not necessarily intended to be run on thousands of material. If you want to scan our entire database, we need something a bit cheaper that is more oriented towards high throughput, and this is the Fermi contour workflow. So here, we are not trying to put an exact number on the conductivity. Rather, we are looking for a descriptor, something that will allow us to compare and rank materials with each other. And of course, to have something cheaper, we need to make a few approximations. And the first one is that we do DFT and DFPT calculations in the neutral system, so that allows us to gain a little bit on the number of K points we use. And then we make a few approximations on the transport. So mostly we just reduce everything to what happens at the Fermi level. And in 2D, what you get is a Fermi contour, hence the name of the workflow. And then we choose only one electronic point on which we're going to compute only one scattering time. And this K point is chosen in the highest velocity direction, which would be the wise direction for transport to use. And then we describe scattering only on the Fermi contour and with a limited number of phonons, usually 5 to 10 phonons. And of course, again, we use symmetries to maximize the cost of the calculation, minimize the cost of the calculation. So this number of 5 to 10 phonons was chosen such that it corresponds more or less to the number of phonons that is already used in our workflows to compute phonon dispersion. This is the same order of magnitude. And this is a little GIF of like this process done on several hundreds of materials. In blue are always the Fermi contours. In green, you don't see them very well because they're often on the Fermi contour, but they're the final states that we consider around the Fermi contour. And in orange are all the possible final states that we have access to using symmetries. Okay, and of course we need to apply to get our descriptor in the end, we apply all those approximations to the expression for the conductivity, and what we obtain is a simple product involving the scattering time, the maximum velocity around the Fermi contour, and the DOS. Okay, and this is our descriptor. So we use this descriptor to rank the materials in our database, and this is the result of this. So in green, I've indicated known materials that are extensively studied in the literature, and all the rest is new. So I apologize for not putting the name of the new ones, but this is unpublished work, and we like to keep a little bit of mystery. So some of the known materials are already praised for their good transport properties. And we see here that at least according to this approximate descriptor, we have found several materials that are better or equivalent. And so this is very encouraging. We have some interesting candidates. In orange are candidates that we selected for further study, so to go through the full transport workflow that is more accurate, more expensive, but more accurate. So those are around 50 materials that we computed did the full calculations for. Again, in green are known ones, and in orange, new ones. Here we are at fixed density of electrons or holes. And of course, the main result of this plot is that we did find several materials with pretty good transport properties. Anything above 10 here is pretty good, and above 20 is very good. And And so for the rest of the talk, I'd like to try to understand what makes those top materials special. Why are they so good at conducting? And one key aspect that is kind of common to all of them, of course, is that they have relatively low electron-phonon coupling matrix elements, and this is captured by our descriptor. But still, if you look more deeply into these materials, you can still distinguish some categories, some types of materials, and we're going to discuss those. We're going to discuss materials with steep and deep single valleys. So those are the case for the green ones that you see here. Then we're going to look at anisotropic Hall valleys. So this is the case for the champion of the database, but also a couple more here. Then we'll discuss the case of this particular material that owes its good transport properties to the fact that its electron-phonon interactions are screened. And this is particularly true for this material, but this is also true to a lesser extent for many materials among those. And finally, we'll talk about this material that is not particularly good initially, but that can be made very good, actually can be made to go into the top 10 by doing some valley engineering. And of course, I'll explain what I mean by that. First, steep and deep single valleys. So a steep single valley, what I mean by that is a valley that is relatively sharp, so it has high velocities. Of course, high velocity is good for transport and conductivity. But it also means low DOS, and this implies that when you dope the material, you're going to fill up the valley pretty fast. And for most of the time, what happens is that you fill the valley high enough that you start reaching other valleys in the band structure. And this is not good, because then you have some intervalley scattering, and the conductivity starts to go down. So a steep valley by itself is not sufficient. You also need it to be deep, meaning that the next valleys in the band structure need to be high enough in energy. And this is the case for indium selenide. If you dope it, say, by 10 to the 13 electrons per centimeter square, you still are well below those other values here that are 0.7 electron volt above. And this is also the case for the second best material in our database here, with a very, very sharp valley here, and all this is high enough. And also, if you think about it, this is also the case for graphene, which has like those Dirac cones that are, of course, very high velocity, and the rest of the band structure is relatively high above this. Okay, the second class are anisotropic Hall valleys, and here I show the example of the whole side of phosphorine. So phosphorine is also good because it has amazingly low electron-phonon coupling, but it does share this feature with a few other materials in the top 20, say. And this is this anisotropy. If you look at the whole pocket, it's not maybe not super clear here, but it's more of a canyon than a valley. It's very oblong. And it also has anisotropic electron-phonon interactions. Here is a plot of the electron-phonon coupling matrix elements. So here we show the coupling between an initial state that is represented by this white star here, and final state that are all those other points here, only in this bucket here. The color of each point represents the strength of the electron-phonon coupling. And here this is plotted for the LA mode, which is the one that couples most strongly in the phosphorine. What we can see, so what this all means is that if you put an electron on the white star here, it will be easily scattered into the red regions and not so much into the blue regions. So what we see here is that the scattering happens mostly on the side, and this is actually not that detrimental to transport as backscattering would be. So this kind of anisotropic electron-phonon interactions is good for transport as well. So seeing this anisotropic band structure and electron-phonon coupling, it's not so surprising to see an anisotropic scattering time here as we go around the Fermi contour. This state is on the Fermi contour, by the way. As we go along it, we can see that the scattering time varies by a factor 2. Okay, so what is good about those materials is that if you choose the right direction for transport, which is this one here, you can benefit from those high value of the scattering time, and you benefit both from the high velocity of those states and the high dust, so which corresponds to this flat part here, that basically comes from the high effective mass in the perpendicular direction. Okay, this material is the one that owes its good transport properties to the fact that its electron-phonon interactions are screened. Its valley is not particularly deep. It's not anisotropic at all. You can see here it's pretty circular. But its electron-phonon coupling is green. Here I show the same kind of plot as before, so showing the electron-phonon coupling matrix element, and I do this for the three phonon modes that couple to electrons significantly. All the rest is relatively negligible. And I do this in the neutral material and in the doped material. As we can see, in the doped material, the electron-phonon coupling is much weaker. So what happens here is that when you put electrons in the conduction band, those free electrons are capable of screening external perturbations like a metal. And in general, not all electron-phonon interactions are sensitive to screening, but it so happens that in this material, all the phonons that couple significantly to electrons are sensitive to screening. And in the end, you end up with a weaker coupling by a factor 2, at least, even an order of magnitude here for this last phonon. And also, the coupling dies at long wavelength, so around this initial state that you see here. And of course, this is good for transport. And this also shows the importance of doing the calculations in the dope material if you want to, so for the transport. All right, and this last category, or just this one material, is a material that is not as good initially, but can be made much better through valley engineering. So this is arsenine. It has a multi-valley structure in its conduction band, as you can see here. And if you look at electron-phonon interactions, you see that they are mostly inter-valley. So this is the same kind of plot as before, this time plotted for all the phonon modes of this material. And it looks a bit different because you have a multi-valley structure, so you have different spots in the Brillouin zone. Now, the white star is a bit small, but I've indicated here that the initial state is always in this topmost valley. And you see that the valleys that light up in red are always valleys others than the one where the initial state is. So that means scattering in mostly intervalley, and this is what limits the transport properties of this material. So we thought it would be nice to be able to kill this intervalley scattering. How can we do it? And we noticed that if you strain arsenine, actually, by a relatively reasonable value of 2%, you can shift 4 out of 6 valleys up in energy, and the shift is large enough that you effectively make those valleys inaccessible for electron-phonon scattering, meaning that the phonon energies are too small to bring an electron from this valley here to this valley here. So you effectively killed intervalley scattering, and this has the effect of enhancing the conductivity by a factor 6 and bringing this material into the top 10 of our 50 materials. So this is great. We would like to do this on other materials. We can think right away at those two systems that are the same structure, basically, but different atoms. But we could also try to look in the database for materials that are dominated by intervalley scattering. And to do that, I use, again, the Fermi contour descriptor that I've described before, and I compute it with or without this intervalley scattering. So it just tricks in the code. You can just turn this on and off. And then I use the ratio of without over with to try to highlight the materials that are dominated by intervalley scattering. And everything that is to the right here can be are such materials, and they would benefit greatly from such valley engineering. Note that we don't necessarily have to use strain to do all this. The basic idea behind the strain is just to break the symmetry and being able to change the energies of the valleys with respect to each other, but we could use other ways to break the symmetry. I don't know exactly which ones, but there are probably more. Okay, and this last slide is about searching for desirable features. And it's actually more about trying to correct the limitations of our Fermi contour descriptor by trying to use more other data. Because I don't remember if I said it, but of course the descriptor is not perfect. It's an approximate quantity, and it misses some things. In particular, it's not very good at capturing anisotropy and screening. It's not very good with anisotropy because the way it's defined, it's kind of an average over the Fermi contour, and so it doesn't fully captures all the subtleties of those anisotropic systems. But we can try to correct for this by using parameters like this velocity ratio. So this is just the maximum velocity of the carriers around the Fermi contour divided by the minimum one. And if this ratio is relatively large, it means that the Fermi contour is relatively anisotropic. And so for those materials on the right here, there could be some our descriptor could actually underestimate the transport properties of our material, and it would be nice to explore a bit more. For screening, our descriptor doesn't do a very good job as well, because you might remember that I said we do the DFT and DFPT calculations in the neutral system, so there is not this doping here, and we don't have screening. And it's not obvious as a post-process step to know which Phonon modes are screened. So it's not obvious to know which ones we can turn on and off with screening. But what we can do is work with this particular kind of electron-phonon interaction, the so-called Fröhlich interaction. That is the coupling with the longitudinal optical modes. Because we know that this one is mediated by electric fields, we know that it is screened, and very importantly, we have an analytical expression for it, so we can take it out of our calculations. So here again, I compute the descriptor, the Fermi contour descriptor, without or with this Fröhlich interaction, and use the ratio to highlight the materials that are dominated by Fröhlich scattering, and that would benefit from screening, because Fröhlich is screened. Okay, so this is like very recent. It's more as an opening to what we can do to go a bit further. That's it. So I've talked about three methods. One to compute electron-phonon interactions in 2D with the proper periodic boundary conditions and the field effect transistor setup. I've talked about a transport workflow for accurate calculations of conductivities in an automated way. I've talked about a more approximate workflow for high-throughput calculations. I've shown a bunch of results. We found several high-conductivity materials, and we've also gained some physical insights into what makes a good conductor. semiconductor. And with that, I'd like to thank Nicola, the rest of my colleagues, the funding, and you for your attention.
Thank you, Thibault. And we have time for questions.
Thanks for the very nice talk. So kind of you based on all these high throughput calculations, so in the end you were able to isolate these particular cases that you were discussing, like steep and deep bands, etc. What kind of features in the band structure would be good for the good transport in these materials? Maybe this is a trivial question, but I'm asking because I don't know. Do you see any obvious correlation between these band structure properties and the actual structure? You know, kind of what chemists would call structure property relation, in a sense that, you know, if you have small or large electronegativity or particular types of symmetry, or I have no clue. So just any thoughts on that?
Well, to be honest, I have no clue either. I haven't looked into that so much, into the chemistry and the structure and the relation with band structure. I usually start with the band structure. So I've started to build up a good intuition looking at just the band structure about what's going to happen, but not looking at the structure, to be honest. But it's interesting, and I can talk with my colleague about trying to do something like this. Yeah.
Thanks very much.
I would like to ask, sorry, this 2D plus FET, that field effect transistor.
Yeah.
So, as a plane wave user, the 2D materials under external field.
Sorry?
The 2D materials under external field.
Yes, yes.
So, can you please put a little bit light on that issue, that how thick compound do you need in order to sense the external perturbation via the external field, or any other?
How thick a compound do you need?
Yeah, in order to apply the external field, which is some periodic potential or something like that. I mean, what is the inside of those technique?
Okay, so more details on the implementation.
Little bit, maybe.
So the material itself doesn't need to be thick. You mean the supercell? How big does it need to be to like have the space?
As well as the material.
All right. So the limitation is more about the cutoff, so the truncation of the Coulomb interactions. From this, you get limitations. I mean, you need a minimum vacuum distance, basically to let the time, let the space to the cutoff to cut everything. So overall, you need as much vacuum as you have material. So you take the thickness of the material, electron density included, double this, and you have your supercell, more or less. Then the gates, that's not so much. That's much less that what you need, the vacuum you need to like have like 10 towards 0 interaction at least, then the gates, they don't take space. They are infinitely thin charge planes. They're just direct deltas of charges.
But under certain perturbation, I would expect some change on the dielectric constant, depending on the type of the amount of vacuum or the amount of the solid in my supercell. Because you are putting external perturbation by field, and you are changing actually dielectric constant.
So you expect the dielectric constant to change?
Change under the certain external perturbation if I change the material thickness, or am I wrong?
So if you change the material's thickness, yes, the dielectric constant
should change probably.
So it's not, as you said, I think earlier, it was a question from you, right?
Yes.
The dielectric constant is not dielectric constant anymore. It's dielectric function is a function of Q. At Q, because Q, we're talking about phonons and stuff, so this is what is relevant here. At Q going to 0, the dielectric constant is actually vacuum. I mean, you just get 1. And then as you go to finite Q, you start having a response from the material. And so the dielectric constant for 2D is more this parameter that tells you when you go from long wavelength to short wavelength regime. So we call it RF, other people call it alpha 2D. There's different names for it. But anyway, this is all included in the DFPT calculations.
Okay,
Yeah.
okay. Thank you.
Cool. Other questions? I guess I have maybe myself a comment just following the first question, that I think these are interesting and probably challenging cases for machine learning. You know, these days we talk a lot about machine learning, and a lot of properties that are machine learned are fairly extensive, you know, the energy, the polarizability. While here we deal with a lot of incidental things that happen in reciprocal space. And so I think it could be, if someone wants to, you know, challenge machine learning, this could be interesting properties to try and predict.
Yeah. So on the machine learning side, here we have not enough data yet, but it might come. But yeah, indeed, like I've been trying to do a little bit of a very basic machine learning, and it's difficult because like those 50 materials, because this is the number we have for accurate conductivity, is a bit light.
Sure. Sure.
I mean, if it was so simple, people would know how to predict superconductors, and they haven't been able for more than 100 years. Electron-phonon coupling is just too complicated. So I think it's hopeless.
So maybe you need things like the Fermi contour descriptor. Yeah.
Okay, so we thank again Thibault. And before giving back the mic to Ian for the last presentation, I'll exploit my last 30 seconds with a mic myself to make an announcement.